Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series.
It is wonderful to be here. And I have to say, looking at the stack of research we have today, I think we are in for something truly special.
I think you're right. Today, we are exploring the ancient mathematical foundations of the modern scientific paradigm.
It sounds a little dry when you say it like that.
It does, doesn't it? But, when we first started looking at this, I was expecting a standard history lesson. You know the drill. Dates, names, maybe a few Roman numerals thrown in for flavor.
Right.
But as I started reading through these sources, the research on trigonometry, the translations of Chinese algebra, the Indian origins of zero, I realized this isn't really history. It's like looking at the source code of our reality.
That is a perfect way to frame it.
Yeah.
The source code.
It's not just about numbers on a page. We're talking about the hidden scaffolding that holds up everything around us. I mean, today we're going to connect clay tablets from thousands of years ago directly to the cybersecurity that protects your credit card.
And that's not an exaggeration.
Not at all. But before we get there, I want to challenge the premise a little bit. We often talk about math as this one thing that just exists, like gravity. But the research suggests it's a technology, right? Something humans had to invent.
Absolutely. We tend to think of this calculating paradigm, this idea that the world can be measured, predicted, and understood through numbers as a product of, say, the scientific revolution in Europe.
Right, like Newton and Leibniz in the 17th century.
Exactly. But the research shows that this paradigm, this way of thinking, has been driving human progress for 5,000 years, from the river valleys of Mesopotamia to the digital cloud.
So what we're really doing today is tracing a genealogy.
We are. We're going to trace the lineage of the technology you use every single day. Your smartphone, your GPS, the internet, all the way back to their roots in ancient Egypt, Babylon, India, China, and Greece.
And what's so fascinating is that things we think are incredibly modern, like binary code or matrix algebra, they're actually ancient, thousands of years old.
They've been rediscovered or refined, but the core ideas, they're ancient. We are, in a way, excavating the logic that built the modern world.
I love that. Okay, let's get into it. Let's start at the very beginning. Part 1, foundations. What we think we know. Why did humans even start doing math? Was it just curiosity? Did someone wake up in a cave and just decide to invent geometry?
It would be romantic to think so, wouldn't it? The lone genius pondering the abstract.
It would make a good movie.
It would, but the reality is much more pragmatic. Math didn't start as a hobby or an abstract art form. It started as a survival mechanism and, frankly, as an administrative imperative.
The administrative imperative. That sounds
Yeah.
so bureaucratic.
It is bureaucracy. I mean, think about the huge shift from hunter-gatherer societies to settled farming communities.
Okay.
When you're a hunter-gatherer, you're constantly moving. You own what you can carry. You don't need complex math. You need to know one, two, and many. That's about it.
But once you settle down,
Everything changes. Suddenly you have a surplus of food, you have grain storage, you have trade with the village next door, and eventually you have kings and empires. And you cannot run an empire if you can't count the grain, tax the farmers, and pay the soldiers.
so you're telling me math was essentially invented by the taxman.
In terms of complex systems, yeah, pretty much. But the cognitive spark, the ability to think that way, goes back even further. We have artifacts like the Ishango bone.
The Ishango bone, right. Found near the headwaters of the Nile. It's, 20,000 years old?
About that, yes. It's incredibly ancient.
I saw the pictures of this. To be honest, it just looks like baboon's leg bone with some scratches on it.
That's what it is, a baboon fibula. But those scratches aren't random. They're grouped very deliberately. Some anthropologists and mathematicians believe they represent a tally system. There's a big debate about what it's for.
A debate. What are the theories?
Well, one theory is that it tracks lunar cycles, which would make it a kind of proto-calendar. But another, more provocative theory is that it shows an early understanding of prime numbers.
Prime numbers. 20,000 years ago. How?
Because one of the columns of scratches features groups of 11, 13, 17, and 19.
Wait, 11, 13, 17, 19. Those are all primes. That feels like a pretty big coincidence for a 20,000-year-old bone tool.
It's a striking coincidence, to say the least. Now, others argue it might be a menstrual tracker, which would mean the first math was actually women tracking their cycles.
That's a fascinating idea.
The point is, we can't know for sure what was in the mind of the person holding that bone, but it proves that the hardware, the human brain's capacity to recognize patterns and quantities, was there. But the software, the systems we use to calculate, That's what really exploded in the Great River valleys.
Mesopotamia, the Nile, the Indus, the Yellow River.
Exactly. That's where the need for bureaucracy really kicked in.
Let's talk about Mesopotamia first. The Sumerians and the Babylonians. This is, what, around 3000 BCE? I was reading about their number system, and it honestly confused me at first. They didn't use base 10 like we do.
No, they used a sexagesimal system, base 60.
Base 60. And this is one of the most enduring legacies in human history, isn't it?
It really is. We live with it every single day.
But why 60? I mean, I have 10 fingers. Base 10 makes intuitive sense to me. 60 seems incredibly cumbersome. Did they have, like, 60 different symbols for numbers?
Not quite. They had a symbol for 1 a wedge and a symbol for 10 a different kind of wedge.
Yeah.
And they'd combine those to make the numbers up to 59. But the reason for 60 is strictly utilitarian. It's genius, really.
Okay, sell me on it.
Imagine you're a merchant in Babylon. You have a big shipment of grain. You need to divide it among your workers or split it with a partner.
I'm with you.
If you use our system, base 10, you can divide the number 10 evenly by 2 and 5. That's it. If you try to divide 10 by 3, you get 3.333 repeating forever.
A mess.
A total mess.
Yeah.
If you divide by 4, you get 2.5. If you divide by 6, it's messy again. You get fractions all over the place.
Right. It's a headache.
Now look at 60. 60 is what mathematicians call a highly composite number. You can divide 60 evenly by 1, 2, 3, 4, 5, and 6, and also by 10, 12, 15, 20, and 30.
Oh, I see. So if I have 60 sacks of grain, I can split them in half, thirds, quarters, fifths, or sixths, and everyone gets a nice, clean, whole number of sacks.
Precisely.
No fights over who gets the .333 of a sack.
Exactly. It was a system built for commerce, for administration, for building. It minimizes fractions. And because it was so useful, it just stuck. I mean, look at your watch.
60 seconds in a minute.
And 60 minutes in an hour.
And a circle is 360 degrees, which is just 6 60s.
We are effectively still telling time and measuring angles like a Babylonian scribe from 2000 BCE. That fundamental structure hasn't changed in 4 millennia.
That is wild. And they were writing all this down on clay tablets, right? I imagine those tablets are pretty durable if we're still reading them today.
Incredibly durable. It's one of history's happy accidents.
Yeah.
If you have a library of paper or papyrus and it burns,
Yeah.
all that knowledge is lost forever.
Right, like the Library of Alexandria.
A tragedy. But if you burn a library of wet clay tablets, you just fire them into ceramic. You bake them and preserve them forever. We have hundreds of thousands of them.
And one of the most famous is known as Plimpton 322.
Ah, yes. Plimpton 322. A truly remarkable artifact.
I read about this one. For a long time, historians just dismissed it as like a practice sheet for a scribe, right? Just a list of transactions or something.
Yes, for decades. It was just seen as a table of numbers. It wasn't until the mid-20th century that people like Otto Neubauer really analyzed the numbers in the columns and realized what they were looking at.
And it wasn't random at all.
Not even close. It's a list of Pythagorean triples.
Pythagorean triples, like a squared plus b squared equals c squared, the thing we all learn in middle school geometry.
The very same. Sets of whole numbers that fit that equation perfectly, like 3, 4, and 5. Because 9 plus 16 is 25.
But the numbers on Plimpton 322 are huge, right? We're not talking 3, 4, 5.
No, we're talking about triples involving numbers in the thousands. This isn't something you stumble upon by accident. It implies they knew the fundamental relationship between the sides of a right triangle.
But wait, the tablet is from around 1800 BCE. Pythagoras lived around 500 BCE. That's a 1,300-year gap.
Correct. More than a millennium.
So Pythagoras got the credit and the fancy theorem named after him, but the Babylonians had already done the homework more than 1,000 years earlier.
History is often written by the victors, or in this case, by the philosophers who wrote the best textbooks later on. The Babylonians used this knowledge for practical things, surveying, construction. They didn't call it a theorem, they just knew it worked.
It was a tool, not a philosophy.
Exactly. Now let's hop over to Egypt, the Nile Valley. They were doing things a bit differently. They didn't use the base 60 system.
No, Egypt used a strict decimal system, base 10, probably for the obvious reason, 10 fingers.
Very likely. But there was a catch, a big one. They didn't have a place value system.
Okay, we need to clarify what place value means because it's so fundamental to us we take it for granted. In our system, if I write a 1 and then a 0 and then another 100, the 1 means 100 because of where it sits, its position.
Correct. The position dictates the magnitude. The Egyptians didn't have that. They had specific hieroglyphs for each power of 10.
Right. I saw this in the notes. The imagery here is fantastic. So a simple vertical stroke is 1. A
Yes.
cattle hobble that looks like a little arch or a horseshoe is 10. A coiled rope is 100.
Yes, and think about that. The coiled rope is the surveyor's tool, which gives you a huge clue about what they used math for.
I see. Keep going, right? A lotus flower is 1,000. A pointed finger is 10,000. A tadpole or a frog is 100,000.
Yes. Well,
And my absolute favorite, for 1,000,000, the symbol is a picture of a man on his knees throwing his hands up in the air. The astonished man.
it's wonderful imagery, isn't it? It symbolizes a number so vast it's almost beyond counting. I am astonished by this amount.
I love that. But doesn't that make doing math incredibly tedious? If I want to write the number 999, I can't just write 3 nines. I have to draw 9 coiled ropes, 9 cattle hobbles, and 9 strokes. That's 27 separate characters.
It was cumbersome for writing, yes, absolutely. But for addition and subtraction, it was actually quite visual and intuitive. You just group the symbols together. If you have 10 strokes, you erase them and draw one cattle hobble. It's very tactile.
It's like using physical money. 10 $1 bills become one $10 bill.
It's a perfect analogy.
Yeah.
But you mentioned the coiled rope for 100, hinting at the popus. This brings us to the birth of geometry.
Geometry, literally earth measure.
And in Egypt, this wasn't abstract. It was life and death. The Nile flooded every single year. It was the source of their life, depositing that rich, fertile soil, but it was also a chaotic, destructive event. It would wash away all the boundary markers between farms.
So every year, the water recedes, and suddenly my farm and your farm. We have no idea where the property line is.
Exactly. Chaos, neighbor fighting neighbor.
Hmm.
To maintain order, the pharaoh employed a special class of people called rope stretchers.
Rope stretchers.
And they used geometry to resurvey the land with incredible precision. They had ropes with knots at specific intervals. They knew that if you took a rope with 12 units and staked it out to form a triangle with sides of 3, 4, and 5 units
You get a perfect right angle. The Pythagorean theorem again.
in action. They used it to ensure perfect right angles for property lines, for the foundations of temples, for everything.
So geometry wasn't invented in a quiet, sterile classroom. It was invented in the mud to stop neighbors from killing each other over farmland.
And of course, to make sure the pharaoh got his correct tax revenue.
Always back to the taxes.
It's the engine of civilization. And they apply this to construction, too. You cannot build the Great Pyramid of Giza without very high-level math.
Impossible. The precision is staggering. The base is leveled to within a fraction of an inch over 13 acres.
It's almost unbelievable. They used a concept called the secant, which is essentially the slope. It's the ratio of the run to the rise.
In modern terms, it's the cotangent of the angle, right?
Yes, exactly. They were calculating the cotangent of the angle of the face to ensure that the 4 faces of the pyramid would meet perfectly at the apex. If you get the seats wrong by even a tiny fraction of a degree at the bottom,
By the time you get to the top, you're off by feet. The sides won't meet.
you'd get a disjointed mess. They also had a very interesting way of handling fractions. The Rhine mathematical papyrus shows they mostly used unit fractions.
Meaning fractions with a 1 in the numerator, so 12, 13, 110, etc.
Exactly. If they needed to represent, say, 25, they wouldn't write 25. They'd write it as a sum of unit fractions, like 13 plus 115. It was clunky, but it was precise for dividing up rations and resources.
It's amazing to think of math as this dirty, hands-on job. Let's move east, China. What was happening there in terms of these foundational ideas?
China developed a very sophisticated, very practical mathematical culture, completely independently. The classic text is the 9 chapters on the mathematical art.
That's a great name. It sounds like a martial arts manual.
In a way, it is the martial art of the mind. And just like the Egyptian and Babylonian texts, it's driven by practical problems: taxation, dividing land, building dikes, managing grain supplies.
So the same problems drive the innovation everywhere.
The problems are universal. But the Chinese approach was very algorithmic. They were masters of the shu, the method, or algorithm.
The algorithm.
Yes. They didn't worry as much about creating an abstract proof for why a theorem worked in a philosophical sense. They focused on providing a clear, step-by-step procedure that gave you the correct answer every single time.
How did they do their calculations? Not with hieroglyphs, I assume?
No, they used something much more dynamic, counting rods on a board.
I read about this. This is fascinating. They had little bamboo or ivory rods, right? And they would arrange them on a grid, like a checkerboard.
Correct. And the way they arranged them was a place value system. Vertical rods for the units column, horizontal for the tens, vertical for the hundreds, and so on.
So they had place value, unlike the Egyptians.
They did. And this physical system allowed them to do something truly remarkable. something Europe wouldn't figure out for many, many centuries. They could handle negative numbers.
Negative numbers. How do you have a negative bamboo rod?
You color code them. They used red rods for positive numbers and black rods for negative numbers.
That's exactly how we talk about accounting today, being in the red or in the black.
The colors have flipped over time today. In the red means debt, but in ancient China, red was often the positive asset color. But the concept is identical. They could visually see that if you have 5 red rods and you need to take away 7, you have to put down 2 black rods. They could calculate profits, losses, debts, and credits visually on the board.
That's a huge conceptual leap.
It's massive.
So we have these great river civilizations. They're building pyramids, they're tracking stars, they're taxing peasants, and they're using some pretty serious math to do it. But then, something changes. A new question starts getting asked. This moves us into our second part, active debate, because there's a major shift in how people think about math. And that shift usually gets pinned on the ancient Greeks.
That is the traditional narrative, yes, the philosophical divergence. While the engineers and administrators in Egypt, Babylon, and China were asking, how do I calculate this? The Greeks, specifically figures like Thales, Pythagoras, and later Euclid, started asking a fundamentally different question. Why is this true?
The birth of the proof.
The birth of the axiomatic method. This is a massive leap in abstraction. It's not enough to show that a formula works for this triangle and that other triangle over there.
You have to prove it logically.
You have to prove, using pure logic and starting from self-evident truths called axioms, that it must work for every triangle that could possibly exist anywhere in the universe, now and forever.
So math moves from being an engineering tool to being a philosophy.
Precisely. Aristotle and Euclid codified this approach. They demanded absolute certainty. They believed that geometry, in particular, was a window into the divine, perfect rational order of the cosmos.
But this obsession with perfection, it led them straight into a crisis, didn't it?
A massive crisis, the crisis of the irrational.
This is the drama with the Pythagoreans, right? They were a bit of a cult.
To put it mildly, they were absolutely a cult, a secretive brotherhood. They had strange rules. They didn't eat beans, they believed in the reincarnation of souls, and their entire worldview was built on one central idea. All is number.
And by number, they meant whole numbers.
Whole numbers and the ratios of whole numbers. Wow. Integers and fractions. They believed the entire universe, from the harmony of music to the orbits of the planets, could be described by these clean, beautiful, rational ratios.
And then someone completely ruined the party.
The diagonal of a square. It's that simple. If you take a perfect square with sides that are 1 unit long and you use their own theorem to calculate the length of the diagonal, the answer is the square root of 2.
Which is 1.41421356, and it just keeps going forever.
It never ends, and it never repeats a pattern. And crucially, it cannot be written as a ratio of 2 whole numbers. It is incommensurable. It is irrational.
Irrational, literally meaning without ratio. I never made that connection before.
That's the mathematical meaning. But to the Greeks, irrational also meant not accessible via reason. This discovery terrified them. It wasn't just a math problem, it was a theological and philosophical catastrophe.
Why? Because it meant their perfect world had a flaw.
Exactly. If this length exists, and you can literally draw it's right there on the square, but it cannot be expressed by their definition of number, then there is a hole in their universe. A chaotic void where their perfect reason fails.
So what did they do when they found this out?
Well, the legend, and it is a legend, is that the man who revealed this secret, a Pythagorean named Hippasus, was on a boat trip with the other members of the Brotherhood. When he proved the existence of irrational numbers, they threw him overboard and drowned him to keep the secret.
Wow. Talk about a hostile work environment. You found a new kind of number? Great. Get in the ocean.
It certainly shows how seriously they took it. But this highlights the fundamental difference in mindset. The Babylonians knew about the square root of 2. They had an approximation for it on a clay tablet that was accurate to 5 decimal places.
They just used it.
They used it to build things. They didn't care that it was irrational. It was a useful number. The Greeks, however, were paralyzed by the philosophical implication. Because they couldn't define it perfectly within their system, they treated it as a second-class citizen. This actually held Greek mathematics back in some ways. They became obsessed with geometry, where you can draw the line, to avoid the messiness of arithmetic.
It's the difference between an engineer and a philosopher. The engineer says, it's close enough to build the bridge. The philosopher says, but what does it mean?
A perfect summary. And while the Greeks were wrestling with the infinite, another, quieter revolution was happening in India, a revolution that gives us perhaps the most important number in history, the number zero.
The battle for zero. This is one of my favorite parts of this story because I think we take zero completely for granted. It's just nothing. How hard can that concept be?
It is surprisingly, profoundly conceptually difficult. You have to make a huge distinction between zero as a placeholder and zero as a number in its own right.
Okay, break that down for us. Placeholder versus number.
A placeholder is just a symbol to show that a column is empty. Imagine an abacus. If you want to show the number 101, you have a bead in the hundreds column, an empty rod in the tens column, and a bead in the ones column. The empty rod is the placeholder.
So it's just a space.
It's just a space. The Babylonians eventually started using a double wedge symbol to show that space. The Mayans had a cool shell symbol. But it was just punctuation. It was like a comma in a sentence. You didn't do math with the comma. You would never say 5 plus comma equals.
Right, it's just formatting to avoid confusion between, say, 25 and 205.
Exactly. The Indian Revolution, which was developed over centuries but really codified by thinkers like Aryabhata and especially Brahmagupta in the 7th century, was to treat zero, which they called shunya, meaning emptiness, as a true number. A number with its own rights and its own rules.
And Brahmagupta actually wrote down the rules of engagement for zero, didn't he?
He did. In his great work, the Brahmasphutta Siddhanta, he wrote down the rules that seem obvious to a third grader today, but were revolutionary then. When zero is added to a number or subtracted from a number, the number remains unchanged.
Okay, that makes sense.
A number multiplied by zero becomes zero, and crucially, a number minus itself is zero. He was defining the properties of this new object.
It sounds like he was defining the physics of a new particle. But didn't he run into some trouble with division?
He did. That's the tricky one. He tried to define $0 in div as $0, which we now know is mathematically indeterminate. And he said that a number divided by zero is a fraction with zero as the denominator. He didn't quite get to the concept of infinity, but he was pushing right up against the boundaries.
But the key takeaway is that by making zero a number, it unlocked a true decimal place value system.
It is the absolute key. Only with zero as a number can you have the elegant system we use today. You can now easily distinguish 20 from 205 from 2. You can perform complex arithmetic without needing an abacus or a counting board. All you need is a stylus and sand or pen and paper.
It's the software update that made modern calculation possible. You can't have algebra without zero. You certainly can't have binary code without zero.
It is the hinge upon which all of modern mathematics turns.
Speaking of hinges and turns, let's talk about angles. Trigonometry. This is another area where different civilizations took different paths to the same mountain peak. We usually give the credit to the Greeks, right? Hipparchus.
Hipparchus is often called the father of trigonometry, and for good reason. He did incredible work in the 2nd century BCE, creating tables to predict the movements of the sun and moon. But the Greek version of trigonometry was based on the chord.
A chord is. If you have a circle, it's a straight line connecting 2 points on the edge.
Yes. The perfect analogy is a bow and arrow. The curved wooden bow is the arc of the circle. The string connecting the 2 tips is the chord. The Greeks calculated the length of that string for various angles.
Okay, that seems logical.
It is, but mathematically the chord is a bit clunky. If you want to use it to solve a right-angled triangle, you have to do a lot of doubling and halving of angles and other manipulations. It's not a direct relationship.
So it works, but it's like trying to run a marathon in hiking boots. It's heavy and inefficient.
That's a great way to put it. The elegant update, the running shoe, comes from India again. Aryabhata, in the 5th century CE, made a crucial shift. He moved from the full chord to the jaya. Jaya also means bowstring, but mathematically he defined it as half the chord of double the angle.
That's the sine function.
It is precisely the sine function we learned in school. He looked at the relationship between the angle and the vertical height of the triangle inside the circle. This simplified the mathematics immensely. It created a much more direct and powerful tool.
So the Indians invented sine.
They did. And then when this knowledge traveled through trade and translation to the great centers of learning in the Islamic world, scholars took it and ran with it. People like al-Battani and later al-Tusi, they added the other functions, tangent, cotangent, secant. They separated trigonometry from its parent, astronomy, and turned it into its own field of pure mathematics.
So it really is a global relay race. The Greeks start with geometry and chords. They pass the baton to the Indians, who refine it into signs. The Indians pass it to the Islamic scholars, who build the full 6-function house of trigonometry.
And that is the very house that we still live in mathematically today.
That's a perfect segue to part 3, frontiers. because we absolutely need to talk about that golden age in Baghdad, the House of Wisdom. This is where things really start to look like modern science.
The Islamic Golden Age, from roughly the 8th to the 14th centuries, was a crucible of knowledge. They weren't just preserving ancient texts, they were actively seeking them out. They gathered manuscripts from Greece, India, Persia. They translated them, synthesized them, critiqued them, and then built upon them.
And the central figure here for mathematics is Al-Khwarizmi.
Muhammad ibn Musa al-Khwarizmi, a giant. His name gives us two of the most important words in our technical vocabulary.
The man whose name is literally algorithm.
Yes. Algorithm is just the Latinized version of his name, algorithmi. And the word algebra comes from the title of his most famous book, Al-Kitab al-Muqtasar Fisab al-Jab wal-Muqabala.
Okay, say that again. Al-Jab.
Al-Jab. The word means something like restoration or completion.
Restoration. That sounds like he's fixing a house or setting a broken bone.
That's actually one of the literal meanings of the word.
Yeah.
And he's doing something similar to equations. Before Al-Khwarizmi, math was often about solving specific one-off puzzles. If I have a field of this size and it yields this much.
Yeah, very practical problems.
Al-Khwarizmi created a general abstract language. Algebra was the process of moving a negative term from one side of an equation to the other to make it positive. To restore it, if you have 6 by Al-Khwarizmi equals $10, you perform algebra by adding 5 to both sides to get 6x. He was creating the universal rules of the game.
So he standardized the process. He made it so you could solve any quadratic equation of a certain type, not just the one about a specific field.
Exactly. He gave us the abstraction. Algebra is the language of modern technology. Without algebra, you don't have physics. You don't have engineering. You certainly don't have computer programming.
And there's another giant from that era, Ibn al-Haytham. He's the optics guy.
The father of modern optics, and arguably the scientific method itself. The Greeks, like Euclid and Ptolemy, had theories about vision. The most popular was the emission theory.
The idea that the eye shoots out rays, like Superman's heat vision, to scan an object.
Precisely.
I always thought that sounded cool, but it's obviously wrong. Otherwise, I'd be able to see in the dark.
That's exactly the kind of logical argument Ibn al-Haytham used. He said if your eyes were flashlights, night wouldn't exist for you. He used rigorous, repeatable mathematical experimentation, which in itself is a huge leap, to prove that light enters the eye from an object. He analyzed reflection, refraction, the geometry of lenses. He effectively described the principle of the pinhole camera.
So every time I take a picture with my phone, every time a self-driving car's sensor identifies a stop sign, we are using the mathematical principles that Ibn al-Haytham laid down 1,000 years ago.
He is the grandfather of computer vision, cameras, and modern sensors.
Incredible. Now, I want to jump back to China for a moment, because while Baghdad was flourishing, the Chinese were working on some forms of algebra that seem, well, impossibly advanced for the time. We talked about the counting rods, but by the 13th century, they were solving systems of equations that would make a modern college student sweat.
You're referring to problems like the crop quality problem and the work of mathematicians in the Song and Yuan dynasties like Zhu Shiji.
Yes. Tell us about the crop quality problem. This isn't just counting sacks of rice.
No. It first appears in the 9 chapters, but it was refined over centuries. Imagine you have 3 types of crop bundles: high quality, medium quality, and low quality. You know, that's say 2 bundles of high, 3 of medium, and 1 of low yield, 39 measures of grain. And you have 2 other similar equations for different combinations.
So it's a puzzle. 2x plus 3y plus z equals 39, that kind of thing.
Exactly. It is a system of 3 linear equations with 3 unknowns. To solve this today, we would typically use something called Gaussian elimination. We put the coefficients into a matrix, and then we add or subtract rows from each other to systematically eliminate the variables one by one.
And the Chinese were doing this when?
The method was there in the Han Dynasty, around 200 BCE, and was perfected by the 13th century. They would set up the counting rods on their board in a grid, which is a physical matrix, and then they would perform the exact same operations. They would manipulate the rods to subtract one row from another. They were doing Gaussian elimination 1,500 years before gas was born.
That is just mind-blowing. It's a completely parallel development of a highly advanced technique, and Zhu Shiji took it even further.
Zhu Shiji developed the 4-element method. He could solve complex polynomial equations with 4 unknowns. He called them heaven, earth, man, and matter.
So x, y, z, and w.
Essentially, yes. He was manipulating these incredibly complex systems on his counting board. It's some of the most sophisticated algorithmic thinking in the world at that time. And we have to mention the triangle.
Pascal's triangle. The one with the ones on the outside, and each number inside is the sum of the two above it. We use it for probability and expanding binomials.
The very same. Blaise Pascal was a French mathematician in the 1600s. But in China, this triangle was depicted by Jia Xian around the 11th century and later popularized by Yang Hui in the 13th. They didn't use it for probability, but for a different advanced purpose, extracting square roots and cube roots of numbers.
So it really should be called the Yang-Hui triangle.
In China it is. It's a perfect illustration of how mathematical truths are universal. Different cultures discover the same beautiful mountains, they just take different paths to get there.
I want to touch on one more frontier before we get to the modern implications, and this one is so unexpected. India and the concept of binary. We think of binary zeros and ones as a computer thing, maybe Leibniz in the 17th century tinkering with it.
But we have to go back way further, to a scholar named Pingala, around the 3rd century BCE.
3rd century BCE.
That's right. And Pingala wasn't a mathematician in the way we think of one. He was a scholar of Sanskrit prosody. He was analyzing poetry.
Poetry. How on earth do you get from poetry to computer code?
It's all about rhythm, patterns, and combinations. Sanskrit poetry is based on the meter of long and short syllables. Pingala wanted to figure out a systematic way to list all the possible patterns of rhythms you could make with a certain number of syllables.
Okay, so if you have a line with, say, 3 beats, how many variations are there?
Exactly. You could have long, 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 short, 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 long, short, long. He wanted to enumerate them all. To do this, he assigned a value to the short syllable, lagu, and the long syllable, guru, effectively 0 and 1. He then created a method for listing all the combinations in order. If you look at his system, it corresponds perfectly to our modern binary counting. 000, 001, 010, 011, 100, and so on.
He created a binary code to categorize poetry.
He did. And he even developed recursive algorithms to generate these combinations. This is the deep conceptual ancestor of the bit, the fundamental idea that any complex information, a poem, a song, this entire conversation, can be broken down into a long string of just 2 simple states.
That's beautiful. The code that runs the entire internet started as a way to understand the rhythm of an ancient chant.
It connects the arts and the sciences in a very profound way. And we should also mention the Kerala school in India. Much later, around the 14th century, mathematicians like Madhava were working with infinite series and concepts that are the bedrock of calculus, centuries before Newton and Leibniz in Europe.
Just incredible. Okay, so we've dug up the foundations, we've seen the debates, we've explored these amazing frontiers. Now let's bring it all home. Part 4, implications. So what? Why does this ancient history matter to you, the listener, driving to work right now?
It matters because we are living completely inside the calculating paradigm.
The calculating paradigm. Define that for us.
It's the fundamental belief that the universe is not random or capricious. It follows rules, mathematical rules. And if you understand those rules, the world can be measured, calculated, and crucially, predicted.
This wasn't always the default way of thinking.
Not at all. For much of human history, the world was seen as driven by the whims of gods, spirits, and unpredictable forces. But the Sumerians predicting the seasons, the Egyptians surveying the land, the Greeks mapping the stars, they started to build this new worldview. They started to believe in a predictable, measurable reality.
And today, we try to predict everything. The weather, the stock market, the spread of a disease, the orbit of a satellite.
Exactly. Let's take satellites as a perfect example. We mentioned the ancient Greek geometer Apollonius of Perga.
Right, the guy who studied conic sections.
The shapes you get when you slice a cone. The circle, the ellipse, the parabola, the hyperbola.
Got it.
When Apollonius wrote his books on conics around 200 BCE, it was the purest of pure mathematics. It was beautiful, elegant geometry for its own sake. It had absolutely no practical application. It was, in a word, useless.
The best kind of math, some would say.
Indeed. For nearly 2,000 years, his work sat there on the shelf. Then, in the 17th century, Johannes Kepler and Isaac Newton are trying to understand the paths of the planets. And they realize they don't move in perfect circles, as everyone had assumed. They move in ellipses.
And comets that swing by the sun and never return.
They move in parabolas, or hyperbolas. The math was already there, waiting for them for 2 millennia.
So Apollonius had solved the physics of the solar system before anyone even knew what the question was.
In a geometric sense, yes.
Yeah.
And today, every single satellite dish on a roof or in a field is a parabola. Why? Because a parabola has a unique geometric property. It reflects all incoming parallel signals to a single focal point.
So without Apollonius playing with cones in 200 BCE, we don't have satellite TV. We don't have the deep space network communicating with probes on Mars.
We use 2,000-year-old useless geometry to explore the edges of the solar system and stream our favorite shows.
That gives you goosebumps. It really does. Okay, what about our digital lives, our music, our photos? We mentioned the MP3 earlier.
This goes right back to trigonometry. Remember we talked about the sine wave, that smooth, undulating wave shape?
The pure tone.
Right. In the 19th century, a French mathematician named Joseph Fourier proved something incredible. He showed that any complex signal, the sound of my voice, a beam of light, a radio wave, can be broken down into a sum of simple sine and cosine waves.
So my voice right now, which looks like a complex, jagged line on an oscilloscope, is actually just a huge pile of smooth sine waves all added together.
That's exactly right. Think of it like a smoothie. When you drink a smoothie, you taste one blended thing. But Fourier analysis is like a magic machine that can unblend the smoothie and give you the exact recipe card. This much strawberry sine wave, this much banana sine wave, this much kale sine wave.
I love that analogy. And how does that recipe card make an MP3?
Well, once the computer has the recipe, the list of all the sine waves that make up the sound, it can look at it and say, you know what? The human ear can't actually hear this tiny little high-frequency banana part. It's there, but it's inaudible. So just deletes it to save space. That's digital compression. That's an MP3. Same for a JPEG image.
So Spotify is just streaming ancient trigonometry refined by a 19th century Frenchman into my ears.
It's all just sophisticated ancient math.
Let's talk about the thing everyone has in their pocket. GPS. I am lost without it. Literally.
GPS is a beautiful symphony of ancient math. It works via a process called trilateration. Your phone listens for signals from at least 4 different satellites orbiting the Earth.
Okay.
Each signal is time-stamped. Your phone's clock compares the timestamp to its own time, and the tiny difference tells you how long the signal took to travel. Since the signal travels at the speed of light, you know your exact distance from that satellite.
And then it just draws circles, and where they overlap is where I am.
Spheres in 3D, but yes, that's the idea. And the math used to solve for that precise point of intersection. It's a 3-dimensional right-angle triangle problem. It is, at its heart, the Pythagorean theorem. $2 plus B2 assistant T22, just with more variables.
So every time I call an Uber, I am relying on Pythagoras.
You're relying on Pythagoras for the geometry and the Babylonians for the incredibly precise timekeeping needed to make it work. But there's one more layer.
What's that?
Albert Einstein. The satellites are moving so fast and are in a weaker gravitational field. So according to his theories of relativity, time literally ticks slightly faster for them than for us on the ground. If the GPS system didn't use Einstein's equations to correct for that tiny difference, the errors would build up and your location would drift by several miles every single day.
It's a mashup of the ancient world's greatest hits plus Einstein.
It is. And finally, let's talk about the security that underpins all of this. Cybersecurity.
This one is surprising. This goes back to Euclid, the geometry guy.
The geometry guy, but also the number theory guy. In his Elements, Euclid gave a beautiful, elegant proof that there are an infinite number of prime numbers.
Primes. Numbers that are only divisible by 1 in themselves. 2, 3, 5, 7, 11, and so on.
Exactly. For centuries, this was a beautiful, but again, useless piece of mathematical trivia.
Yeah.
Who cares how many primes there are?
Right.
But today, the security of our entire digital world RSA encryption, which protects your bank details, your emails, your credit card numbers online, relies on a simple fact about primes. It utilizes what's called a trapdoor function.
What is a trapdoor function?
It's a process that is very easy to do in one direction, but practically impossible to do in reverse unless you have a secret key. Imagine mixing 2 colors of paint. It's trivial to mix red and blue to make purple.
Easy.
But if I give you a bucket of purple paint, it is chemically impossible for you to unmix it and give me back the original red and blue. That's a trapdoor.
Got it. So what's the mathematical version of that?
Multiplication versus factorization. If I take 2 massive prime numbers, each one hundreds of digits long, and I ask a computer to multiply them together, it can do that in a fraction of a second.
Okay.
But if I give the computer the result, that huge product, and I ask it, which 2 prime numbers did I multiply to get this? The computer's only option is to start guessing, to try dividing it by every prime number it can think of. It would take all the computing power on Earth longer than the age of the universe to figure it out.
And that difficulty, that impossibility of unmixing the numbers is what keeps your secrets safe.
Exactly. The security of the entire global economy rests on a property of numbers that an ancient Greek was playing with for intellectual pleasure in 300 BCE.
It's humbling, isn't it? We walk around with these supercomputers in our pockets, feeling so modern, so advanced. But the language those computers speak, the binary from ancient India, the algebra from medieval Baghdad, the logic and geometry from ancient Greece, it was all written by people who worked with clay, papyrus, and bamboo.
It really is. We are standing on the shoulders of giants from every corner of the ancient world.
It makes you realize that math is the only truly universal language. It transcends culture, it transcends time. The vocabulary of our future AI, space travel, quantum computing, it was written in our distant past. We are just now, finally, learning how to speak it more fluently.
And that is why we study the stacks, to see where we came from so we can have some idea of where we are going.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support. And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content. And support us on Patreon. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.